Duobinary encoder. In part 1 of our lecture, we have seen that frequency response. We have obtained expression for frequency response and we have plotted this. In this session, we will see how to find out the response in time domain or the impulse response. So for that, you will start with the expression in frequency domain. That is, we know the transfer function of the overall system of a duobinary system is given by h Nicosit into this is the response of the duobinary encoder. That is 1 plus, your output of the duobinary is ck. ck is given by ak plus ak minus 1. Okay, so you have the response is 1 plus e raised to minus j 2 pi ftb. Okay, this is cascaded with the h Nicosit, ideal Nicosit channel. So your overall duobinary response is h Nicosit into 1 plus e raised to minus j 2 pi ftb. I just opened the bracket, so what will you get? H Nicosit of f plus h Nicosit into e raised to minus j 2 pi ftb. Now you have to get it impulse response, that is in time domain. So this I write it in small h. So h Nicosit of capital F, again in time domain, that I represent it as small h. Similarly, h Nicosit into e raised to minus j 2 pi ftb. This is actually the time shifting property. Okay, so we can write it as small h of t minus tb. So I have H1, the overall H1 of t. H1 of t is the overall impulse response of your duobinary encoder. Okay, so that you can write it as overall frequency response of the duobinary signaling system. Okay, the full system, that is including the encoder as well as a ideal Nicosit channel, that is given by H Nicosit of t plus H Nicosit of t minus tb. So what is actually H Nicosit of t? We have already know the ideal Nicosit channel. So this was the frequency response of the ideal Nicosit channel, non-zero value from minus w to w, and impulse response was a sinc function. Okay, sinc function, that is given by 1 by tb sinc of t by tb. Okay, so H Nicosit of t, I can write it as 1 by tb sinc of t by tb. So what will be H Nicosit of t minus tb? You just replace t by t minus tb. So sinc of t minus tb by tb into 1 by tb. This 1 by tb is common to both the terms. Okay, then you have the expression in the form sinc of x. What is sinc of x? Sinc of x, I can write it as sin pi x by pi x. Okay, so you have sinc of x, so I write it as sin pi x by pi x. Similarly, here again you have a term in the form sinc of x, so you can write it as sin pi x by pi x. Okay. Now to solve this, what I do is the first term sin pi tb by tb by pi tb by tb written as the same. Then you have the second term. In the second term, you have what you have done is you have the term like this, pi into t minus tb by tb. This tb I just move to the bracket, so that what will you get? Pi t by tb minus of tb by tb is 1. 1 into pi is common. Okay, so you'll be having pi t by tb minus pi. So the numerator will be pi t by tb minus pi. Similarly, so for the denominator, move that tb to the bracket, you will be having pi t by tb minus tb and tb will cancel, so minus pi. So again the denominator will be pi t by tb minus pi. Now you have the term like this. So here the term is sin of pi t by tb minus t. You know sin of minus theta. You know sin of minus theta equal to minus sin theta. So you can use this here. So here you have sin of pi t by tb minus pi. So I take a negative sign outside. So this one I can just reverse. Okay. So sin of pi t by tb minus pi, I can write it as minus of sin pi minus pi t by tb. Okay. Now you have sin of pi minus pi t by tb. What is this term? Sin of pi minus pi t by tb. So if I have sin theta, sin, what will be sin of pi minus theta? Okay, sin theta. What is sin of pi minus theta? Sin of pi minus theta actually lies in the second quadrant, is it? So it lies in the second quadrant, and you know the rule, all silver tea cups. That is in the second quadrant, sign is positive. So what will be sign of pi minus theta in this pi minus theta? That will be equal to sin theta. So this sign of pi minus pi t by tb, I can simply write it as sin of pi t by tb. Okay, so this is the next step. We have done sin of pi minus theta as sin pi t by tb. Now we have to solve this one. So in order to solve this one, what I have done is, here I move the tb to the numerator. So what will you get? Tb into sin pi tb by pi t. Then here again I take the tb as common and move that tb to the numerator. So I'll be get tb into sin pi tb by then pi t minus pi into tb, is it? So pi t minus pi into tb. Now I will take the common denominator of these two terms. Okay, so I have pi from this term I can take pi as common, pi of t minus tb. So what will be my common denominator? Pi into t into, here I have t minus tb. Okay, so take it as a common denominator. So what will I get? Here I have to multiply it with t minus, here I have to multiply it with t minus tb, is it? So here I have only pi t. So I have to multiply the numerator by t minus tb. So multiplying with the t, I have tb into t into sin pi tb by tb minus tb, t minus tb. So tb into this term. So you'll be having tb square sin pi t by tb minus, what about this? I have pi into t minus tb is already there. So you have to multiply it with t. Okay. So you'll be having minus tb into t into sin pi t by tb. So you just solve for this. Just solve for this. This tb into sin pi tb by tb and this one minus tb into t into sin pi t by tb will cancel out. So what is left is, you have tb square, that is minus tb square sin pi tb by tb by denominator. Okay. So in this term you have a term minus. Okay. So this minus I can remove by replacing this term, that is t minus tb as tb minus t. Okay, so this minus I can remove by replacing the denominator as tb minus t. So what is my term now? tb square into sin pi t by tb by then what I get here is t pi t, that is, this is the term. So what I get here is, I just take the minus sign, I just leave. So minus sign as just leave. So in my denominator I will be having pi t into tb minus t. Okay, so that is the expression we obtain here. tb square into sin pi t by tb into pi by pi t into tb minus t. So this is the impulse response of your duobinary signaling scheme. Okay, so now you can plot it. So you just see your expression. So this is the expression for your signal, that is sin of pi t by tb into tb square by pi t by tb minus t. So when you plot it as a function of time, you find out the value for t equal to 0. Find out the value for t equal to 0. Substitute t equal to 0, you will get the value as 1. Substitute t equal to tb, you will get some non-zero value. Substituting t equal to tb, that is in your expression you substitute t equal to tb, again you will get a non-zero value. Then substitute t equal to 2 tb, you will get the value as 0. Okay, so this is the impulse response of your system. So just plotting this as a function of time. So what is evident from this figure? Just see the impulse response show two distinguishable values at the sampling instant. Or you can see that when you take the impulse response, it is spread over more than one signaling interval. Is it? That is at tb it is having a non-zero value. At 2 tb only it is having the value 0. So it's spread over more than one signaling interval, or it is known as partial. So the response in any signaling interval is actually partial. That is, when you consider only this interval tb, the response is only partial. So it is known as a partial response signaling. And so it is a partial response. So that is why we call it as a partial response signaling. And you can also see the tail decays only as a factor of 1 by magnitude of t square. The tail decays only at a factor of 1 by magnitude of t square. So this is the impulse response of a duobinary signaling.